Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we discussed few important issues related to the fundamental of consolidation, and we have seen two different types of soil. One is normally consolidated soil, another one is over consolidated soil, and at this moment we are quite familiar to these two terms, right. So, what is normally consolidated, what is over consolidated, and how to find out this pre-consolidation pressure which will govern or which will tell about the state of the soil, whether it is over consolidated or whether it is normally consolidated, right. So, these are the few things we have discussed in the last lecture. So, today we will be obtaining the calculation of settlement from 1D primary consolidation. So, let us consider a saturated clay layer of thickness capital H and cross sectional area capital A under an existing average effective overburden pressure sigma naught prime. Okay. So, we are considering one clay deposit which is completely saturated, whose depth or the thickness is H and cross sectional area is A, and it is under existing average effective overburden pressure sigma naught prime. Now, because of an increase of pressure say delta sigma prime, so this sigma naught prime was there. Okay. That was the initial starting point of the calculation. Now, because of an increase of pressure delta sigma prime, let the primary settlement be SC. Okay. So, if that is true, then delta V, that is the change in volume, is nothing but V naught minus V 1, where V naught and V 1 are the initial and final volume of the soil deposit, is equal to HA. HA is nothing but the height thickness into cross sectional area, that will give me the initial volume, minus H minus SC. So, that is the changed or the reduced thickness of the soil deposit, because once you are applying some delta sigma prime on top of the soil deposit, it will undergo some volume change, and that volume change is proportional to the change in thickness as well. Already we have discussed this thing in the last lecture, because you are providing some confinement in the lateral direction. So, H minus SC is now your new thickness of the soil deposit, where SC is the settlement, that means the deformation or the change in your thickness. Okay. So, H minus SC into A. So, that will give me the final volume V 1. So, which will give me final expression as SC into A. So, SC into A is nothing but delta V, which is nothing but the volume change, okay, or change in volume. Now, the change in total volume delta V, already we have seen, that is equal to SC into A, and which is equal to V V naught minus V V 1. What is V V naught? V V naught is the initial void volume, and V V naught is the final void volume, because whatever volume change you are going to observe, so that is simply the volume change in the void space, right. So, the change in volume of void is nothing but the change in actual volume of the soil deposit, because soil grains or the soil solids are not going to exhibit any volume change, right. Already we have discussed this thing. So, V V naught minus V V 1 is nothing but the volume change, that is the initial void volume minus final void volume, which is equal to delta V V. So, that is nothing but the change in void volume. Okay. So, change in volume is nothing but equal to change in void volume. So, now we know from our fundamental definition of void ratio that delta V V, that is a change in void volume, is nothing but equal to delta E into V s, where delta E is the change in void ratio, right. So, we know that E is equal to V V by V s, if you recall. So, basically delta E, that is a change in void ratio is nothing but equal to change in volume divided by the volume of solid. So, delta V V is nothing but equal to delta E into V S, right. So, from this I can write V S is equal to V naught by 1 plus E naught, that we can establish from our previous say definition whatever we have covered for our void ratio and other things. So, V S is nothing but the volume of solid is equal to V naught, okay, divided by 1 plus E naught, right. V naught is the volume, I mean initial volume, is equal to A H, that is the initial volume, already we have seen, that is A is the cross section area and H is the thickness, and 1 plus E naught, right, where E naught is the initial void ratio at V naught. So, when you have the volume of soil is V naught, at that time your void ratio is E naught. So, we can establish this equation 4.13. So, equation 4.12 and 4.13, basically these equations are not new to you, these equations already we have covered, we have discussed and established earlier. So, from equation 4.10, that means 4.10 to 4.13, basically what we are getting, delta V is equal to S C into A, okay, is equal to delta E into V S, right, is equal to A H divided by 1 plus E naught into delta E, right. So, from this I can find out, or I can write S C, that is the primary consolidation settlement, S C is equal to H into delta E by 1 plus E naught. So, I mean this is the expression by which I can find out the primary consolidation settlement in any soil deposit. So, you need to know the initial void ratio E naught, you need to know the volume change, that is nothing but the change in void ratio, that is delta E, and you need to find out or need to observe the thickness or the initial thickness of the soil deposit. If you know these three parameters, you can find out the consolidation settlement S C. Now, based on different conditions, whatever we have covered like normally consolidated or over consolidated, you will be getting the different expression for S C, we will see that. So, but the backbone expression of S C is 4.14. Now, for normally consolidated clay that exhibit a linear E log sigma prime relationship, already we have discussed this thing, that you will be getting some steep slope with linear relationship when the soil will be behaving as normally consolidated soil. When the soil will be behaving as over consolidated soil, at that time you will be getting rather flatter slope and some non-linear portion. Well, so delta E is equal to, in case of normally consolidated soil, what is your delta E? Delta E is equal to C C into log sigma naught prime plus delta sigma prime minus log sigma naught prime. So, this is basically, if you recall your E log sigma prime curve. So, basically this was the portion for normally consolidated soil. So, basically from this you will be getting, so your delta E is nothing but, so this is your say sigma naught prime and this is your sigma naught prime plus del sigma prime. So, from there I can establish, so delta E is equal to some constant C C into log sigma naught prime plus delta sigma prime minus log sigma naught prime, right. So, that we can establish from this plot, right. So, that we are getting here. Okay. Now, what is C C? C C is a constant, right. C C is a constant, that is nothing but the slope of the E log sigma prime plot and is defined as the compression index. So, that is known as compression index, and you please remember these terms, because frequently we will be using these terms later on when we will be talking about different issues related to the consolidation. So, compression index is nothing but the slope of E log sigma prime plot under normally consolidated soil condition. Therefore, S C can be written as C C into H by 1 plus E naught. H by 1 plus E naught is nothing but delta. So, if you go back to this expression, so your delta E S C is equal to H into delta E by 1 plus E naught, right. So, instead of, in place of delta E we are putting this expression, and we will be getting Sc equal to Cc into H by 1 plus E naught into log sigma naught prime plus delta sigma prime by sigma naught prime, right. So, basically in case of normally consolidated soil, if you want to find out the 1D primary consolidation settlement, basically you need to know what was the initial effective stress, and then after incremental load, because you are going to find out the settlement for some increment of load or the increment of pressure, right. So, that increment of pressure, if you know the delta sigma prime, okay, if you know the initial thickness of the soil, if you know the initial void ratio E naught, okay, these are the things can be obtained, right, or can be observed or can be determined, and Cc is the constant, some constant we will find out, or we will see that how to find out this constant. So, if you know these parameters, you can find out the primary consolidation settlement in the normally consolidated soil. Okay. Now, for over consolidated clay, what will happen? So, for over consolidated clay, you have to basically two different regions. One region is that when sigma naught prime plus del sigma prime, that is the increment of the total pressure, is less than equal to the pre consolidation pressure sigma c prime. At that time, soil will be behaving as complete over consolidated soil. Am I right? So, basically if you recall your E log sigma prime plot, so basically this is the something like this. So, you are basically if you have this condition, so this is basically your say sigma c prime. Okay. So, you are within this region. So, if you are within this region, then that means whatever I mean increment of load or whatever total enhancement or increment is happening in the application of the load, that is well below the pre consolidation pressure. So, soil will be behaving as over consolidated soil by definition, right. So, in the over consolidated clay, delta E is equal to Cs some constant, okay. We will see that what is Cs, Cs into log sigma naught prime plus delta sigma prime minus log sigma naught prime. So, it is as simple as that, I mean, because this is the linear relation again, you have the linear portion, this portion is linear portion, but that is under over consolidated part. So, this linear portion can be defined by this expression. So, now if I put the expression or the I mean equation for delta E, then we will be getting Sc is equal to Cs into H by 1 plus E naught into log sigma naught prime plus delta sigma by sigma naught prime. Now, what is Cs? Cs is nothing but slope of rebound curve, that is the unloading curve, right. Basically that part whatever I have shown you, that is the unloading part, right, slope of the rebound curve, and is defined as swell index. That means you are allowing the soil to swell, that means whatever load you have applied, now you are coming back, right. So, Cs is known as swell index. Now, in case of if you have the second region, so as I told you that in case of over consolidated soil, you will be having two different regions. One region is that when you are below the pre consolidation pressure and when you are above the pre consolidation pressure. So, if you are if you are I mean within the or above the pre consolidation pressure, that means sigma naught prime plus del sigma prime is greater than sigma c prime. At that time, Sc is given by this part. So, Cs into H by 1 plus E naught log sigma c prime by sigma naught prime. So, this part will give you the settlement due to your rebound curve or the over consolidated part, and this part will give you normally consolidated part. Okay. So, this 4.17 will give you the total settlement for over consolidated soil when your stress increment or the load increment is greater than the pre consolidation load. So, Skempton 1944 suggested, now we will find out this compression index Cc, because these are two constants we have just now observed, that compression index Cc and soil index Cs. So, now we will find out how to find out these index or these constants, right. So, Skempton 1944 suggested for compression index for undisturbed clays, Cc is equal to 0.009 into WL minus 10. What is WL? WL is nothing but the liquid limit, already you know, right. So, if you know the liquid limit of that clay, you can find out Cc, which will be constant for that particular type of soil. Similarly, the soil index is appreciably smaller. Soil index, as I told you, because you will be getting some flatter slope. Cc will be much more higher than Cs, because in case of normally concentrated soil you will be getting some steeper slope, whereas in case of over concentrated soil you will be getting some flatter slope. So, Cs is associated with the over concentrated soil. So, the soil index is appreciably smaller in magnitude and is given by Cs approximately equal to 1/5 to 1/10 of Cc. Okay. So, now you can see, I mean, what will be the order of Cs. So, Cs is much more lower than Cc. Now, coming to the secondary consolidation settlement, as I told you, you will be having two different type of consolidation settlement. One is the primary consolidation settlement, another one is the secondary consolidation settlement. So, in case of secondary consolidation settlement, let's find out when you will be having or when you will be exactly talking about secondary consolidation settlement. So, basically you have the curve like that. Okay. So, initial flatter part, then the steeper part, right. In this part you will be having some steeper slope, and then basically after this point, basically you will be getting some flatter, I mean curvilinear part. So, now basically if you extend this straight line part and this straight line parts, you will be getting some point here. So, from this point onward you will be getting some secondary consolidation. Okay. So, now let us find out the secondary consolidation. So, here actually if you see this is with respect to time. So, void ratio versus time plot in log scale. So, this is T1 at T1 whatever void ratio was there, at T2 this is the void ratio. So, your difference in void ratio is delta E. So, you can establish, right, the equation for this part or this secondary consolidation part. So, let us see what is the equation. C alpha, that is the constant, already we have seen in the last figure, that is C alpha. Okay. So, that is nothing but the slope of this line in the secondary consolidation part. So, C alpha is equal to delta E by log T2 minus log T1, agreed, just now we have seen. So, that is nothing but delta E by log T2 by T1. So, the magnitude of secondary consolidation can be calculated as, so this is the secondary consolidation settlement SS is equal to C alpha prime into H into log T2 minus T2 by T1. So, where C alpha prime is nothing but C alpha divided by 1 plus EP. Okay. So, it is, I mean the expression for the settlement will be remaining same, whatever we have discussed, right, H into delta E by 1 plus E naught. E naught is the initial void ratio. In case of secondary consolidation, what is the initial void ratio? That is the final void ratio of the primary consolidation, because once you cross the primary consolidation, then only you will be entering the secondary consolidation part. The final void ratio of the primary consolidation will be the initial void ratio of the secondary consolidation. So, here in this expression EP is void ratio at the end of primary consolidation and H, capital H is the thickness of clay layer. So, if you know these things, so you can find out. So, at you observe some time T2 and T1 and you find out C alpha prime, you know H. So, you can find out secondary consolidation settlement, right. So, secondary consolidation settlement is dependent on time. So, as you, because that will be happening throughout the life of the structure. So, it may happen. So, immediate settlement or the primary settlement will be happening based on the primary consolidation. After that, the secondary consolidation will be always there and secondary consolidation settlement will be negligible. I mean, we will come to that point. So, secondary consolidation settlement is more important than primary consolidation in organic and highly compressible inorganic soils. So, please try to remember secondary consolidation settlement is more important. Okay. It will be giving you some significant value in case of organic as well as highly compressible inorganic soil. So, the soil which is highly compressible, that means even after the primary consolidation you will be observing some significant amount of secondary consolidation. However, in most of the cases in over consolidated inorganic clay, the secondary compression index is very small and of less practical significance. So, that is why people generally, for most of the general cases, people only calculate the primary consolidation settlement and based on that they design the whole structure, right. Say, I mean the secondary consolidation will be much more lower than the primary consolidation settlement in case of normally normal soil, right, over consolidated normal soil. So, in case of that type of soil, your primary consolidation has to be given more emphasis than the secondary consolidation. So, that is why people are not that much interested to find out the secondary consolidation settlement, because it depends on time. So, as the time goes on, you will be observing some amount of settlement. However, if you are dealing with organic soil or highly compressible inorganic soil, then you must think about the secondary consolidation, and you must calculate the secondary compression or the secondary consolidation settlement, right. And then based on that you need to design the structure. So, if you design the foundation in organic soil or highly compressible inorganic soil, you need to take care of the settlement even under secondary consolidation. So, that I mean to say. Okay. So, that basically you need to think about. So, first you do some experiment and then you find out what type of soil you are dealing with, then you go for whether you will consider the secondary consolidation settlement or whether you ignore the secondary consolidation settlement. Now, time rate of consolidation. Now, Terzaghi in 1925 proposed the first theory to consider the rate of 1D consolidation for saturated clay soils. Okay. Now, we will try to develop the 1D consolidation theory. Okay. Based on that, we can calculate the consolidation for a particular deposit, okay, under completely saturated situation. Now, what are the different assumptions? Now, the clay water is homogeneous. So, the clay water is homogeneous means the clay is completely saturated, that means you do not have any kind of different types of fluid present in the soil. So, whatever water is there, that is completely homogeneous and clay is completely saturated. Saturation is complete, as I told you, the complete saturation is required. So, you do not have any partially saturated soil. So, if you deal with partially saturated soil, what will happen? Because of your air will be taking care of, or air will be occupying some amount of voids. So, that voids will be behaving in a different way than the voids which will be filled with complete water, right. So, that is why the consolidation theory is based on completely saturated soil. If you have partially saturated soil, you will be having something else. So, that is not the scope of this particular course. However, you need to most of the times you will be finding out the settlement or the consolidation settlement, which will be under that situation the soil will be completely saturated. Okay. Then compressibility of water is negligible. So, that means water is completely incompressible material that you are considering, and that is that will be a good say assumption. There is no problem in that. So, we know from our mechanics point of view that water is incompressible material, and therefore, the compressibility of water, if we neglect in the determination of the consolidation theory, then there will be no harm. Then fourth one is compressibility of soil grains is negligible. So, frankly speaking, you will be getting some, if you go for some higher load application, basically you will be observing that some compressibility is happening in the soil soil fabrics or the soil particles, but that compressibility is very say negligible as compared to the compressibility of the soil matrix as a whole. So, that compressibility of soil grains, each individual soil grain is negligible, and hence we are not considering that thing in the determination or in the analysis. Then fifth one is the flow of water is in one direction only. So, when we are talking about the 1D consolidation theory, when we are trying to develop or establish the 1D consolidation theory, basically the flow of water is in one direction. So, you can have the flow in different directions, right, all three directions you can have the flow, but that we are not considering for understanding the 1D consolidation theory. So, that can that could come in case of when we are talking about the 3D consolidation theory, at that time 3 direction flow you are considering, but however, that is not the scope, or that is beyond the scope of this particular course. Then the flow is not turbulent, okay. The flow is laminar, therefore, the Darcy's law is valid. So, whatever law you have observed or you have established in case of permeability of soil, so that Darcy's law is valid. That means, V, that is the velocity, is equal to K, that is the coefficient of coefficient of permeability, into I, that is the hydraulic gradient. So, that equation is valid, and based on that we can establish the 1D consolidation theory. So, thank you very much. So, I will stop here today. So, in the next lecture we will talk about, or we will see, or we will establish the 1D consolidation theory. Thank you.